This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 6 of Week 4. The affinity laws, the most frequently tested pump calculation on the exam. They tell you how flow, head, and power change when you spin a pump faster or trim its impeller. The whole topic rides on one pattern. Flow scales with the first power, head with the square, power with the cube. Get those three exponents right, and you own this section. Why they matter. A manufacturer tests a pump at one speed and diameter and publishes one head versus flow curve. The affinity laws slide that curve to any new speed or diameter without retesting. They answer the two questions the exam loves. Slow a pump down, what happens to flow, head, and motor load? Trim an impeller, does it still hit the duty point? This is why variable frequency drives save energy. A small speed cut gives a large power cut, since power follows the cube of speed. And the laws are dimensionless ratios, so units cancel. You only need consistent units when you finally compute power. The most common case, a speed change at fixed diameter. Flow rides the speed ratio to the first power, head the square, power the cube. So double the speed and you double the flow. Quadruple the head, multiply power by 8. The cube is the headline, cut speed in half, and power drops to 1/8. The memory hook, QHP, maps to 1, 2, 3. Write that ladder in the margin before you touch a number. Hold this picture, 3 bars, flow, head, power. All stretch with the same speed ratio, but flow to the first power, head the second, power the third. The longer the bar, the higher the exponent, so power swings the most for any change in speed. Flow short, head medium, power long. The whole topic in one glance. The other lever. Change the impeller diameter at fixed speed, physically trimming it on a lathe. Same exponents. Flow first power, head squared, power cubed. Only the ratio changes to diameter. Trimming is a permanent fix to dial a pump down, but stay within about 10 to 15% of full diameter. Beyond that, the impeller no longer fills the casing, and efficiency falls off. So speed change is reversible and instant. Diameter change is permanent metal removal, but the math is the same ladder. Both change at once. Multiply the two ratios inside each exponent. Flow gets the product to the first power, head squared, power cubed. Nothing new, still the 1, 2, 3 ladder on the combined ratio. The clean way is to form the combined ratio as a single number, then raise it to 1, 2, or 3. Don't square and cube the pieces separately. That's where slips happen. Every affinity law problem rests on one hidden assumption. Efficiency stays essentially constant as you scale, the 2 points being dynamically similar. That holds for modest changes near the best efficiency point. Speed within about 20%, trims within 10. Push past those and efficiency drifts. For the exam, treat it as constant unless the problem gives a second value. And one subtlety, because efficiency is held constant, the power cubed law already includes it. Don't divide by efficiency twice. The variable table, speed n and diameter d, given at both states. Flow scales as the ratio to the first power, head as the square, power as the cube, and efficiency is assumed constant. The scaling ratio is the speed ratio, the diameter ratio, or their product. Each output raises it to its own exponent. Speed in RPM and diameter in inches cancel inside the ratio, so no conversion is needed for the affinity step. Worked problem. A centrifugal pump runs at its best efficiency point with a fixed impeller. At 1750 RPM, the duty point is 600 GPM, 95 feet of head, 20 horsepower. A variable frequency drive slows it to 1400 RPM, diameter unchanged. Find the new flow, head, and power. The plan: form the speed ratio, apply the 3 laws, and check that all 3 dropped. Form the speed ratio once. 1400 over 1750 is 0.8. Raise it to each exponent. Flow gives 480 GPM, head about 61 feet, power about 10.2 horsepower. Look at the payoff. A 20% speed cut gave a 20% flow cut, a 36% head cut, and a 49% power cut. Power nearly halved for a modest speed reduction. The variable frequency drive payoff in one calculation. The exam also runs the laws backward. Say the same pump must deliver a target 540 GPM. Find the required speed. Flow is linear in speed, so invert the flow law. Baseline speed times the flow ratio gives 1575 RPM. Because flow rides the first power, the flow ratio maps straight to the speed ratio. Only then do you square for head and cube for power. One caution, match the right quantity. Target a head, take a square root. A power, a cube root. Now the traps, led by the most common pump error on the exam. 1. Swapping the exponents. People square flow or cube head and lose the point. Lock it in, flow first, head second, power third. Write QHP maps to 1, 2, 3 before any arithmetic. 2. Dividing by efficiency twice. The power cubed law already assumes constant efficiency, so apply it to shaft power directly. 3. Matching the wrong quantity in reverse problems. A flow is linear, a head takes a square root, a power a cube root. 4. Forgetting the trim limit. Trims beyond 10 to 15% break the constant efficiency assumption. 5. Pushing speed beyond about 20% leaves the similar operating point band, and the estimate degrades. Bookmark the pages. The affinity laws themselves, all three exponents for speed and diameter. The combined form just multiplies the two ratios. The pump power equation where the cube comes from, since power goes as flow times head. And the centrifugal pump characteristics, the head flow curve you're scaling. The affinity laws page is the highest yield page in the hydraulics chapter. Fold that corner. You now own the highest yield pump calculation, the 1, 2, 3 affinity ladder for flow, head, and power, under speed changes, diameter trims, and both at once, forward and backward. In Topic 7, we move to the pump's suction side, net positive suction head, and cavitation. We'll build the suction margin in absolute pressure terms, compare available against required, and see why a pump that scales beautifully on paper can still cavitate if its inlet is starved. See you in Topic 7.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.